The median is the value that lies at the center of an ordered data set. When the observations are arranged from smallest to largest, the median divides the data into two equal halves. 50% of the observations are at or below the median, and 50% are at or above it. How the median is computed depends on whether the number of observations is odd or even. For an odd number of observations, the median is the single middle value. For an even number of observations, the median is the average of the two middle values. Because the median depends only on the order of the data and not on their numerical magnitudes, it is said to be resistant to extreme values. Large outliers may change the mean substantially, but they have little or no effect on the median unless they alter the ordering of the central observations. This resistance makes the median a particularly useful measure of typical when distributions are skewed or contain outliers. Florence Nightingale is well known for her work in improving hospital conditions for British soldiers during the Crimean War. One dataset she examined recorded outcomes for soldiers treated in hospitals in Crimea and in Scutari, Turkey. The data contains the number of soldiers hospitalized in various regiments and the number who died. Consider the number of soldiers who died in Scutari for the first 5 regiments, with an extreme observation of 500 included. There are 6 observations, so the median is the average of the third and fourth values in the ordered list. The third value is 94, and the fourth value is 96. Adding these two values together and then dividing by 2 gives the median as 95. Unlike the mean, which was pulled upward by the extreme value of 500, the median remains close to where most of the data lie. This robustness is why medians are often preferred for skewed data such as incomes, house prices, or medical costs, where a small number of unusually large values are common. Now consider a data set that contains fuel efficiency in miles per gallon for various automobiles tested in the 1970s. Suppose we examine the fuel efficiency of the first 11 cars in the data set, an odd number of observations. Because there are 11 observations, the median is the 6th value in the ordered list, which is 21. This value represents the fuel efficiency of a typical car in this subset. Even if one of the cars had extremely poor or extremely high fuel efficiency, the median would remain stable unless that extreme value crossed the center of the ordered data. This example illustrates why the median is often reported for performance measures like fuel economy, commute times, or household expenses, contexts where a few extreme cases should not define what's typical. The median answers the question of typical by focusing on position rather than magnitude. Its resistance to extreme values makes it a reliable measure of center for skewed distributions and data sets where outliers are common. The mode of a data set is the value that occurs most frequently. Unlike the mean and median, which describe the numerical center of a distribution, the mode describes what is most common. Because it depends only on frequency, the mode can be used with categorical, ordinal, and quantitative data. A data set may have one mode, called unimodal, which is a single most frequent value, 2 modes, called bimodal, which often indicating 2 distinct groups, or more than 2 modes, called multimodal, suggesting additional structure or heterogeneity. The mode is especially useful for categorical variables, such as favorite color or blood type, and discrete quantitative variables, such as number of visits or number of children, where identifying the most common outcome is meaningful. In these contexts, the mean may not even be defined, and the median may be less informative. For continuous variables measured with fine precision, however, exact ties are uncommon. In such cases, the numerical mode may not be meaningful or may not exist at all. Instead, we often identify the mode visually as the peak of a histogram, representing the most densely populated region of the data, rather than a single repeated value. Suppose a dental clinic records the number of visits made by each of 30 patients over the course of a year. The variable is a discrete quantitative count. We can find the mode by identifying the most frequently occurring value, which is easily identified with a frequency distribution. In this data set, the most common number of visits is 2, making 2 the mode. Interpreted in context, this tells us that the typical patient visits the clinic about 2 times per year, not in the sense of an average, but in the sense of what happens most often. And this is a situation where the mode is particularly informative. Patients and administrators may care most about the most common pattern of usage rather than a numerical balance point. Now consider a data set on fuel efficiency measurements for many car models. We examine highway miles per gallon for a subset of vehicles. Because highway fuel efficiency is measured on a continuous scale, exact repeated values are not especially meaningful. Instead, we identify the mode as the peak of the distribution using a histogram. From the histogram, we see that the highest bar occurs around 28 to 32 miles per gallon, indicating the modal region of the distribution. Rather than a single numerical value, the mode here represents the most common range of highway fuel efficiency among these vehicles. This approach is typical for continuous data. The mode is interpreted as a region of highest density rather than a single repeated observation. The mode answers the question, what value occurs most often? It is indispensable for categoricals data, useful for discrete counts, and informative for continuous data when interpreted through histogram peaks. While it does not use all the information in the data the way the mean does, the mode often aligns closely with how people intuitively think about what is typical.